the unit on differentiation with the power rule. So one of the ways that someone comes about thinking that there should be a rule to make this go faster is they say, let's say we did a bunch of these using our definition of the derivative. So the limit as h goes to 0 of f of x plus h minus f of x all over h. And you did the first one, and you got an answer that the derivative was 2x. Then you did x cubed, and you got an answer that the derivative was 3x squared. And you did x to the 4, and you got a derivative of 4x cubed. And what a mathematician might do is, after doing a bunch of these, go, it seems to be that there's a pattern happening. What is that pattern? And can I use that pattern to predict other things? So you get to 3x cubed, and you're like, ooh, this one's a little bit different. It's got a 3 in front. And the derivative happens to be 9x squared. And then you're like, oh, I want to try some with negative numbers. And you tried some with negative exponents. And we get a derivative of that. And here, with a number in front and a negative, we get those as derivatives. So we have to say, do we see some patterns already? How is it, like, what about the exponents? What do you notice about the exponents in all of these ones compared to the exponents that we started with? It's 1 less. Does that work even with the negatives? Yes, because if you subtracted 1 from -2, you would get to -3. Okay? So it appears that the exponent is 1 less. What do we notice about the number in front? Well, it started off being the same as the exponent, right? But then how do we get that 9? And then here, it worked out to be the, so it looks like if there's no number in front, it's the same as the exponent. What kind of pattern happens for when there is a number in front? So we think about that for a little bit. Okay? And then look at some more examples, see if the same thing happens. Well, now we get to some that are a little bit tricky, but what could you do with the square root? Square root is the same as x to the half. And the derivative, does it still follow the rules? This is the derivative. Does it follow the rules with fractions? Did we subtract 1 from the exponent? Yes. And that number, when there was nothing in front, the number happens to be in front. This one, could you write that as an x with an exponent? Yes. Right? X to the 0 would just be 1. The derivative of that one is going to be 0. Does it follow the rules? That one we'll have to think about after. This one, you could write this as following the rules by subtracting 1 from the exponent, but anything to the power of 0 is equal to 1, so 7 times 1 would be 7. Cube root is x to the 1/3, and sure enough, this one seems to follow the pattern. By the way, in this unit, you're going to get really good at subtracting 1. That doesn't sound like a very hard thing to do, but here, you see how I subtracted 1 from 1/3 and got -2/3? That's a little bit harder subtracting 1 than it is to do 3 minus 1. And if you have a square root on the bottom, this is the same as 1 over x to the 1/2. And your exponent rules would say that's the same as x to the -1/2. And does this one follow the rule as well? Yes, it does. Again, you're going to get good at subtracting by 1. Now, some of these in the future, you're not going to take the extra steps. Like in this one, when you have just a number and you're finding the derivative, you're just going to say that it's equal to 0. You're not going to change it to 5x to the 0 and then use your rules, right? Your rule technically would say 0x to the negative 1, and 0 times anything would be 0. But we have a couple of important patterns to notice. One is that the exponent goes down by 1. Whenever you have a power, and this is why it's called the power rule, your exponent goes down by 1. The other thing we haven't completely figured out is the number in front. Like, why is this a 9 when there was a 3 in front? How would you get 9 from that? Well, one of the things you noticed in the first 3 is the exponent came out in front, right? 2, 3, 4. Technically, there was a 1 out in front. And if you did 2 times 1, you'd get 2. 3 times 1, you'd get 3. 4 times 1, you'd get 4. Can you see that this 9 that you could get by multiplying the 3 when it comes out in front by the 3 that's there? And this negative 12, that negative 3 comes out in front, multiplies by that 4, you get negative 12. And so we can summarize all of these things into our constant rule and our power rule. Yes?
For the last page,
Yeah. This one right here.
for the y equals 5,
Yes?
because it's technically 0, x to the minus 1 would
That would be,
no derivative for x equals 0.
that's like this, right?
Yeah.
So the derivative would be 0. Oh, like
Like as
if you had this as your start, the derivative would be 0 as well. Because you could think of it as 0x to the 0, and it would still follow the rules.
it'd be 0x to the minus 1, and it's extra go on bottom. So
But it'd still be 0. Right, because the x isn't 0. Just this, the numerator is 0. But we don't have to worry about that as much as saying that any time, I mean, this is how it's connected to the power rule, and that explains why any constant would equal 0. Okay? Now, the constant one, right, if we go to the constant rule, this is the easiest one to prove with the definition of the derivative. If I used my definition, limit as x goes to 0 of f of x plus h minus f of x all over h. Okay? What is, limit as h goes to 0? If f of x is equal to c, can you see that your numerator would just be c minus c? The x plus h wouldn't make a difference. And if your numerator is equal to 0, anytime a fraction's equal to 0 in your numerator, your answer is going to be equal to 0. So technically, you get limit as h goes to 0 of 0 over h. And that's going to equal 0. This, the power rule, is a little bit more complicated to prove. And so I'll let you look that up if you'd like, right? Because if you started it off with your definition, you would have the limit as h goes to 0 of x plus h to the n minus x to the n over h. And this is big to expand. Okay? Right? If you expanded x plus h squared, that's not so bad. X plus h cubed is a little bit worse. And as we go higher and higher, they get worse and worse. Oh, Now I'm getting tempted to prove it. Do you want to prove it? So if you kept going, x plus h to the 4 and x plus h to the 5, and so on and so forth, okay? You could expand these using your binomial theorem and Pascal's triangle, okay? Now Pascal's triangle, remember, looks like this. Okay? And what Pascal's triangle means is that if you took one of these, like x plus h to the 4, x plus h to the 4 would have 5 terms, and you would use this row of Pascal's triangle. And you would get, just for that example, you would get an x to the 4, okay, plus a 4x cubed h plus a 4x squared, a 6x squared h squared plus a 4x h cubed, and then plus 1 h to the 4. Remember doing that with binomial theorem? Now what's going to happen when you subtract x to the 4? This one's going to always cancel out. Whatever the biggest one is, it's always going to cancel out. All of the other ones have h's in them. When you factor out the h, right? If I factor out the h and I have the h on the bottom, those h's will cancel out. Once you factor out one h, does it make sense that only this one is going to be left without an h? All the other ones would have an h in them. Okay? So then applying the limit, all the other ones go to 0, and you would just be left with 4x cubed. Taking the 4 out in front, subtracting 1 from the exponent. So if I did the limit as h goes to 0 of this one, this would start off with an x to the n, and then minus an x to the n minus 1 h, then plus, dot, 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 forever, until it gets to h to the n. And then it would have minus x to the n there and h. So in university calculus, this is where a lot of students feel like this is going to be the most complicated thing I've ever seen, because the professor is going through this proof and there's like, I can't write everything down, I have to do dot, 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 and hand waving to try to explain all of these things, connecting to the binomial theorem, which you've since forgotten from high school, and you feel like, I'm not going to be able to do this. Well, it's not that bad, okay, because we'll get to the rules, and then after that in university as well, you just have to use the rules and have the odd proof here and there. But with this, these x to the n's, whatever the highest power, cancels out, just like the x to the 4 would have canceled out. And in each of these terms has an h, which you could factor out, an h out of the top, leaving you with n x to the n minus 1, plus, and then you're going to have all these other numbers, but they will all have, they'll all have an h in them. And so when these cancel out and you apply the limit, the only thing you're left with is the nx to the n minus 1, which is the power rule. I wasn't going to go through the proof of it, but sorry, got a little carried away. The proof, though, once it's done, this means that we can apply the power rule from now on as a shortcut. And so if you have something like, what's the derivative of x to the 7? Well, it's just going to be 7x to the 6th, and it's going to be that easy. The other thing I wanted to talk about in this one, so I'm going to erase this for now, is some notation things. So, power rule. If y equals x to the n, then the derivative, so this is the symbol, y prime is one of the symbols for the derivative that we've seen already, is equal to bring the number in front and subtract 1 from the exponent. Okay? For all real numbers n. So that means this works with positive numbers, this works with negative numbers, fractions, decimals, it works for all numbers. Okay? And the notation here, mathematicians are notorious for not liking to write a lot of things. So for all real numbers n seems like too many words to write. Have you seen this notation before? N belongs to all the real numbers. So that's a shortened way of saying that. And here is your new symbol for the day mathematically, an upside down A, because it takes too long to write for all. Oh. So there's your new mathematical symbol for the day, for all. Do you like the short form mathematical symbols? Okay. I really like, my favorite one in university was this one. If. This means if and only if. It's stronger than just your regular if. If and only if you can symbolize with if. So it means that this works if this condition is true, and this condition has to be true for this to work. It can't work only like if this works, then sometimes it works, but it can work in other times too. It's like a weak if. This is like a strong if. If and only if. Anyways, so I'll introduce you to weird mathematical symbols as we go along, but I like the for all. For all n belonging to the real numbers. And then we have our constant multiple rule, which is really just saying that if you have a number in front of a rule, you already know that number doesn't affect it. So for example, here, I talked about having x to the 7. The derivative, according to the power rule, is 7x to the 6th. So if I had 5x to the 7, what am I doing? I am just multiplying x to the 7 by 5, a constant. This is where the constant multiple rule comes into effect. Having that 5 there means that I can do the derivative, and I'm going to say you'll never show it this way, but for now I'm going to, right? What's the derivative of x to the 7? It's 7x to the 6. What would that 5 do in front? Well, that 5 would just multiply by the 7, and you'll have 35x to the 6th as the derivative. What are you going to do when you do this derivative? You're going to do that step all at once. You're going to say, okay, I know that my 7 is coming out in front. Well, there's a 5 there. 7 times 5 is 35. And then subtract 1 from the exponent. So, different notations. Find dy dx. That means find the derivative of this equation. Is that enough time to get the answer? Everybody's got the answer? Want to check to see how you did? Did you get, now if the notation starts that way, I'll write dy dx equals, did you get negative 15x to the 4? You got 7. Uh-oh. And we have some issues. Could you do this with the definition? Yes. How long would this take us using the definition? A while, because you would have to do x plus h and expand it to the exponent of 5. Not very much fun. Doable? Yes. 5, 10, probably a 10-minute question, maybe. How long did it take us? 3 seconds, maybe less. Makes it really quick. So when we have our power rule, we can find the derivative really quick. Okay? And so on your limits test next week, I'm going to probably have a power rule 1. You have to use the definition of the derivative. You're going to look at the question and know the answer immediately, and then have to still show all of your work. So that's just the way it is. It should almost be not allowed to have this class before we do our test. So you have, oh, this is the way I have to do it. Because now even that homework sheet that you've been working on, you'll want to be doing the shortcut every single time. Okay? Yes, that is the beauty of it, is you know if you're right. If you get the final answer and you're like, okay, I got it right. The danger is when you know the right answer and you're not doing the right math, and then you start to like, oh, pretend a little bit here, pretend a little bit there. How many people did that on an identity once? Yes, a little bit of, oh, it's not working, but I'll just pretend something. I'll pretend something else, and look, it works in the end. Yeah. That's a little disastrous. Ooh, a medium level one. And again, I'm just trying to introduce in the language of the question different ways to ask the same thing. This one, again, is asking you to find the derivative. Okay? So one of the things, as far as notation goes, we can introduce let y equals 4x to the 8. One of the things the grade 12 course is particular on is not introducing new variables without defining them. So there's no y in this question right now, but if I say let y equal that, then I can use the notations that I like. Well, I'm going to take one extra step. This is a medium one. This right now isn't in the right form to do the power rule, because the x to the 8 is in our denominator. And our power rule only works when we have a power not in a denominator, just a regular power. But I can use my knowledge about exponents to change that x to the 8 in my denominator to an x to the negative 8, which would be a regular power in my numerator. And now I can bring this negative 8 out in front. Okay? Now, how do you, when you multiply, like I'm going to have to multiply that negative 8 by 3/4. I'm going to do that off to the side here. How do you multiply fractions? Like, what's the basic rule for multiplying fractions? First of all, would you make this a fraction as well? Ooh. Negative 8 over 1. And then your basic rule for multiplying fractions is you multiply your numerators, right? And you multiply your denominators. So we could do that step, and you would get negative 24, okay, over 4. And then you could divide, right? And you would get negative 6. So we're all good to say this is going to be a negative 6 out in front. And subtract 1 from the exponent. And be very careful here, because subtracting 1 is not hard. But some of you will do minus 8, and you'll subtract 1, and you will get minus 7. Can you see yourself doing that? Never? Quickly erased it. It's so easy that your brain goes, oh, 8 minus 1 is 7. You should write 7. You have to be very careful, because your brain will love to play tricks on you that way. Now, the reason I put up the fraction stuff there is that is the proper way, or one of the proper ways to multiply fractions, but it has some downfalls. Okay? I am going to get you to multiply some fractions here. 17 over, haven't decided yet, times by 19 over 3. Oh, some people are smiling. Is your 17 times table not your best? Okay. What happens if this was a 19? 17 over 3. Okay? Good. Now, how many people did 17 times 19 is 323? And 19 times 3 is 57. And they're like, oh, they both can be divided by 19, so I should reduce that to 17 over 3. No? No? Nobody did that? Good. I'm glad. Because you could see right away that those 19s can simplify, right? Using those mental math kind of things really help, because when I bring this negative 8 in front, I'm like, ooh, negative 8 divided by 4, I'll do that first. That's negative 2 times 3 is negative 6, right? Rather than going to negative 24 divided by 4, if you can keep your numbers small, you're going to make less mental math mistakes. And possibly less mistakes in general. And you could go faster dealing with small numbers. That's not to say that I don't think it's a good skill to know that 17 times 19 is 323.